Hi everyone, this is Sandong Kim, and today we're gonna present the ARC challenge and the events we had, including Happy Arc Day, and the possible approaches that we can tackle this ARC problem. So I prepared this presentation with Prince, Subin, and Sheikh. So let me briefly show some examples of the problems there we are solving for. So here's step 3 ARC problems. So our aim is to find the pattern existing in these training examples, and then use that pattern to find the answer of this test example. So when you see the first example, you can see that there are 3 objects located in the black grid space. And the output grid here, you can see that all objects are aligned horizontally. And you can find out that the location of that objects follows the location of where blue objects currently exist. And for second problem, you can see there are multiple objects in the grid space, and you can find out that the output grid represents the object that appears the most in the input grid space. So this is the most common objects that exist in the input grid space. And the last one, you can see that there are 4 colors, and each colors are mapped to the pattern that exists in the larger part of this grid space. So for each color, you should fill in that color to four different quadrants of the grid space and 4 different quadrants of the larger objects. So here are the answer of these questions. And the difficulties of this problem is that each problem have different pattern inside, considering that you have like 100 examples as a training set and find some pattern existing, it might be difficult to generalize that pattern to the new task that you're gonna see afterwards. So the goal is to build a human-like AI which can do abductive reasoning. And abductive reasoning is to sense of reasoning, which begins with an incomplete set of observation. And we have to proceed that pattern to the likeliest possible explanation for the set so that we can generate the output grid by understanding those patterns in the training examples. So today we prepare the agenda. First, we'll remind you the background of the ARC challenge and the concept of intelligence. And then second, we'll summarize what we have done during the past event, Happy ARC Day. So we first created the data set called Mini ARC, and we also developed a tool, O2R tool, to solve our problems and log human trajectories. And then we'll briefly explain what kinds of principles that we need to have by designing solutions of this problem. And primitives here is the word which says the basic operators of solving like this kind of problems. And we'll next present 3 potential approaches. The first one is to apply transformer into the problem that we are solving for. The second one is inverse reinforcement learning. And the third one is the recent work done by KAIST, and they use logic-guided reasoning for solving a similar problem called Raven's progressive matrices. So I'll give this floor to Prin, and he's gonna present the ARC challenge and the measure of intelligence.
Okay, so the ARC sort of challenge originated from a paper called On the Measure of Intelligence, written by an AI researcher by the name of Francois Cholet. And it was released in around late 2019. And basically, he starts off by talking about a couple things, and we're going to just go through the main points that he brings up. The first main point is the distinction between skill and ability and how intelligence relates to these two concepts. So skill basically talks about a measure of experience, which means that basically what you've been learning to do, you're being tested on. Let's say that you're learning how to integrate stuff in calculus. On the exam, you're being tested on problems that are similar to what you've practiced on. because your goal is to measure experience. Ability, on the other hand, measures something different. It measures flexibility. It measures how fast you can adapt to new tasks. So you're not going to be tested on what you've learned exactly. You're going to be tested on how to learn something else that's related to what you've learned. So back to the calculus example, if you've learned single variable calculus, to measure your mathematical ability, you might be asked to learn multivariable calculus. It's related to what you've learned, but it's not exactly the same. And Francois Chollet basically argues in his paper that intelligence is more about ability. When we say that someone is bright, we don't mean that they've done a ton of problems and they can quickly integrate something. What we mean when we say that someone is intelligent is they're able to quickly and efficiently acquire new skills based off of what they've already learned. And that brings us to the second main point of the paper, which is the definition of intelligence. And the intelligence of a system is defined to be a measure of its skill acquisition efficiency over a scope of tasks with respect to three things. That's priors, experience, and generalization difficulty. So the first part, skill acquisition efficiency, that's what we just talked about. We don't want to measure skill. We want to measure the ability of someone. But what's a bit harder to understand is what he means when he says with respect to priors, experience, and generalization difficulty. So I'll just explain this with some examples. When we think of priors, I want you to think of comparing the performance between a convolutional neural network and a multi-layer perceptron. Let's say that we train both of these on the same image set, and then we test it on the same test set as well. And both of these gets 95% accuracy. Which one do you think is more intelligent? Some people might say that, okay, well, they got the same accuracy, so that means that they're equally intelligent, right? But in this case, I actually argue that the multi-layer perceptron is more intelligent than the CNN. Why is that? It's because the CNN has certain prior knowledge that's baked into it that MLP doesn't have. For example, CNN has the idea of translational invariance baked into it. It also understands that pixels that are close together affect each other more than pixels that are far apart. And that's very useful for image recognition. So in this case, MLP is more intelligent because it's able to achieve the same thing as CNN, but it has much less prior knowledge. So that's what we mean by priors. Next, we talk about experience. So I want you to think about GPT-3, Generative Pre-trained Transformer 3, and let's compare its performance to a newborn version of itself, which we'll call GUT3, Generative Untrained Transformer. And let's say that we give it a prompt and make it write some sort of essay. Of course, GPT-3 writes a very beautiful, eloquent essay, whereas GUT3 writes garbage. Can we truly say that GPT-3 is actually more intelligent than GUT3? Well, the answer is no, right? Because they're literally carbon copies of each other. In terms of intelligence, in terms of potential, they're basically the same. It's just that one has more experience than the other. If you give the untrained model the same experience as the pre-trained model, they're both going to achieve the same performance. So when we talk about measuring intelligence, we have to keep in mind that experience matters. Finally, difficulty. This one's pretty self-explanatory. If you have two models, one you test on the MNIST dataset and one you test on the ImageNet dataset, and it turns out that one model performs 95% accuracy on MNIST and the other only 93% on ImageNet, you can't say that the first model performs better than the second model because MNIST is a significantly easier task than ImageNet. So in this case, you should control the difficulty between tasks in order to measure intelligence properly. And all of this eventually accumulates in the ARC dataset. But before we go there, we have to talk about some things. So experience and difficulty, we sort of understand. But what priors do we need in order to create human-like AI? Well, these priors are going to be something that humans all have, right? We have to assume that for a human-like AI, the prior that we need is something that humans inherently already know. And in the paper, they outline 4 things. The first is objectness. As humans, we understand that the world is composed of distinct objects that are able to interact with each other in a predictable way, meaning that the world is made up of objects, and objects have a certain idea of physics imbued into it. The second prior knowledge that we have is agentness. What this means is that some objects possess a will and they can act upon it to achieve a certain goal. If we have two objects and we observe that one object moves toward the other, we'll probably assume that one object is pursuing the other. That's agentless. The third one is about numbers, which means that we can compare two quantities of numbers. For example, even kids knows that 3 apples is less than a dozen of apples. So we have some notion of numbers and we can do some basic arithmetic with it. Lastly is geometry. We understand that you can take an object and you can sort of rotate it or flip it and it remains the same object. So these are the 4 priors that all humans inherently have. And we want our AI agent to understand these 4 priors as well. And keeping all of this in mind, we come up with a data set that basically uses those 4 priors and also tests how fast an agent can acquire new skills, because every single task tests a different type of skill. Okay.
So before moving on to like the second part, like happy arc day, like do you have any like questions on the definition of intelligence? Oh, nice. So this slide like visualizes like some examples that the inventor Francois Chollet proposed when writing their paper. So there are around 400 training data set and 400 evaluation set and 200 test set. And some of them are hidden so that only competition participants, so that only like the inventor of this data set can access and evaluate the performance of the intelligence that participant made. So Happy Arc Day. So we threw a 2-day event called Happy Arc Day to spread awareness of artificial general intelligence and this challenge. And we also share how our team works to the members in our groups. And we develop a mini arc data set contains like 150 examples of similar data. So here it is. So we have invited around 15 participants, and we created like some data set by using the tool that we designed. And we also solved some of this problem. And these tools, you're gonna see some videos like recording how we can solve this problem and how we can create the data set. And we also spend some time on evaluate each data set in terms of difficulties to human and difficulties to developing a program. And also we measure the creativeness of each problem. And the second day, we set up some time to program, like to set up some time to imagine like what kinds of possible approaches are there. And we let our participants to program like some method to solve some problems. They felt it's difficult to generalize this to like unseen like task examples, unseen test examples, even though it follows the similar pattern. So we kind of get some consensus that how difficult it is to come up with an algorithm that we haven't seen any like task example so far. So this is a mini arc data set. So there are 2 examples that our members like submitted while doing this event. The first one is simple color fill. So you can see some objects here, and you have to fill the middle of the objects by finding that there are some other like colors inside. So the main purpose here is to generate a data set which is concise and compact enough compared to the original data set proposed. So we confine the grid size into 5 by 5, input and output grid size into 5 by 5, but still we are able to gather a lot of creativities inside. You can also see the second example, which demonstrate like biggest objects like attracts every other objects in the grid. So let me show how we like collect the data set and how we solve this problem using our tool by open the video we have. Mm. Can you see the video here? So this is how we solve the problem by using the tool. So the left-hand side, you can see some examples. So there are 5 training examples. And this is how we are kind of like how human can find the problems and patterns inside these examples. And now I figure out the solution and trying to copy each objects into the layer function by using the layer function over here. And the solution is to swapping the place of each objects, and we submit after we design the final output grid. So this is how we solve the problem, and each actions are saved into the logs, like human demonstrations. And we're gonna use like some of these logs to develop an AI that can imitate how humans solve these problems. So I also solve the other problems. And like, as I mentioned, like each actions are saved into edges in this state space graph. So each node here represents like what kinds of current state it is. And each edge each edge means the actions between 2 different states. So for each problem, we can construct this state space graph. So we would like to analyze this graph and find out what kinds of new actions that we would like to add in our tools and what kinds of important actions that we should be used for synthesize the final program. And this is the part of designing the mini arc problem. So to make the event fun, you prepare some tips when we are designing like these problems. And this is how I generate a new examples. So the idea here is to expand the colored pixel on the right down side of the corner. And the yellow line here, I just consider it as a boundary point. So maybe you'll figure out what kinds of patterns that I think of when I design this example. And what kinds of priors does this example follow? Number?
The object.
Objectness. And to make open set like test cases, I also use this red color for the last 2 examples of this problem. And after I make all the examples, then I can submit this task into our database, and then the staff members will evaluate how creative the problem is and how difficult the problem is to human and AI. And also we ask them to describe what kinds of pattern exist in this problem. So these are some queues of problems that were waiting for like our approval. And after the problem is approved, then will become the mini arc benchmark data set. So during the event, like we measured the amount of successful like task that each participants made of, and we gave some small prizes to the winners. And those are some like interesting like examples that we collected during the events. And here are the evaluation form. And we would like to do this to raise the quality of the data set we collected. So we are able to collect like currently around 200 responses to evaluate like what kinds of benefits inside in our each problem. So we intended to make most problem that can be easily solvable by human, but may not be directly solvable by like intelligence. So see the curve that people find out that most of the problems, the pattern inside is obvious, or at least like very easy. But when we see the amount of difficulties for computers, we can see that there are more like examples. People felt it difficult to build a program. Even though we build a single program for each specific example, they feel slightly more difficult. And if you're considering of developing a intelligence to generalizable to like every problems, that is even more difficult. And this is a distribution of how people think of each how people think creativeness of each problem. And you can see that there are even though the examples are easy, they feel they're very creative in terms of like openness of the problem set. And we also spend some time on reviewing some of the existing works. So some other works tries to make the detailed description of each problem and provide those description to language model and try to use them to build a program. So we also collected some description of each problem. And even though human can use their perceptions and find the pattern without really like describing it detailedly, so you can have your like different like how human can find pattern easily. So that is difficult to describe, like visual.
So even if we intuitively understand the solution, it's pretty hard to put them into words.
Yeah, maybe because human can use like all the visual cues and have all the priors inside, so they can somehow figure it out directly. But when you describe this problem into paragraphs, sometimes it takes a long time to describe. That's what I wanted to say.
Also, like even when like humans are trying to communicate with language, so they're using analogies like there's a tail over there, or it looks like a flower vase. So people are using abstract concepts that are only understood by another human. So it gets even more difficult to communicate that to computers.
Yeah, so some like words
Yeah,
can be explained in different ways, but most of the human can understand that word by looking those examples, but maybe like AI model cannot. Yeah, that is the main difficulty by using this description to generate like program that can solve these tasks. So I'll move back to my slide. Can you see my slide or not?
Yep.
Yep, okay. So this is what we had during the happy hour day. And now I'll give a floor to Subin to describe how to solve ARC with program synthesis.
As summarized before, the agenda of solving ARC is to solve different problems with different rules with one system. Let's say that there's task 1 containing rule 1. We can train neural network 1 to solve task 1, but if we give task 2 as input to network 1, it will give an output applying rule 1 to task 2, which is not the desired output. Here, we can learn insight of what we really need to make, a system that can learn new rules when new task is given as input. Basically, it's a system that can learn how to learn rules. To achieve this goal, we can introduce Dreamcoder, which is a program that uses program synthesis to solve tasks. Program synthesis is useful because it can produce new programs for every new rule, but the system that produces the new program is the same. To evaluate, these are the steps of Dreamcoder. First, the Dreamcoder synthesizes an initial program for the given input, which is a set of primitives and task X. Primitives are the basic units of code that can be used as building blocks to produce new programs. In ARC test cases, it may be something such as flip, rotate, color, or etc. Next, the Dreamcoder analyzes the synthesized programs and tries to find similar structures of codes from the two different programs. If there are similar structures of codes, the Dreamcoder pulls out the structure and adds the structure as a new primitive. This starts from the idea that if there is a good primitive, then it would appear frequently in different programs solving similar tasks. Then the Dreamcoder reuses this new set of primitives to synthesize a better program for the same task X. By iterating this process, Dreamcoder combines primitives to produce new set of primitives, which means that Dreamcoder is able to abstract the tasks and find new ways to solve a problem. As in, it's like giving a rock and wood to the system, and it is able to produce a hammer that can be used to build more complex structures. To give practical example, this is the example of the new primitives that the Dreamcoder was able to produce. The above 6 lines are each a solution for 6 different ARC tasks made from 4 primitives that was given as input. The solution are programs that were initially synthesized by Dreamcoder. From these 6 programs, the Dreamcoder was able to make 3 different functions below. If you take a look in the top box, the first 2 solutions have similar structure. Dreamcoder was able to catch this common structure, and it derived a new function below, where the function in the red boxes are replaced with $0, where any action can be applied. It is similar with the next 2 lines and the last 2 lines below. In the paper applying Dreamcoder to ARC, they provided Dreamcoder with 6 primitives such as vertical, flip, rotate, clockwise, or etc. They trained the agent on subset of 36 ARC tasks involving symmetry and iterated Dreamcoder 5 times. The agent showed improvement as iterations progressed, and it solved 17 to 19 to 22 tasks. And the below functions are the new primitives that the Dreamcoder was able to abstract. We also conducted an activity during the Happy ARC Day abstracting primitives. We instructed the participants to come up with primitives that could be generally used throughout ARC tasks. These are the following primitives that the participants were able to come up with, which includes finding rectangles, find area with same color, find fixed sized object, find largest objects. And these are some other primitives that other teams came up with. And these are the common primitives that came up with. Which is finding object by color, finding largest or smallest objects, or such primitives that can be easily thought of to use in general ARC problems. These are human thought primitives, but we are hoping that AI can teach itself such primitives.
So we would like to move to the next part of this presentation. So Subin, Prin, and Sheikh will present like 3 possible approaches. Like one is inverse reinforcement learning. The second is RL by applying transformer, which is called decision transformer. And the third one, there are similar problem called Raven's progressive matrices, and one KAIST team presented logic-guided reasoning to solve this problem in principled way.
So one of the approaches is inverse reinforcement learning. When an agent is trying to reach a goal state, it will do a sequence of actions that will change the state and ultimately reach the goal. During the process, we can give reward to the agent, indicating whether the action is optimal. Through these rewards, the agent will be able to form an optimal policy deciding its actions. We call this process reinforcement learning. Reinforcement learning is learning an optimal policy when a reward function is given. However, inverse reinforcement learning is learning the reward function when an optimal policy is given. By a given optimal policy, it means expert trajectories such as human demonstrations. Basically, inverse RL is a method to train an agent so that it can mimic human demonstrations. The benefit of IRL is that it can learn complex actions with small amount of data. Also, IRL model tries to learn what the trajectory is trying to do, which is helpful when the expert trajectory is imperfect. One of the basic algorithms using IRL is apprenticeship learning via IRL. When given an optimal policy from expert trajectory and initial reward function phi and initial policy of the learner, we loop the following algorithm. We first find the pi I through initial reward function and calculate the value from both pi star and pi I. Then we try to find the parameter theta in the reward function that maximizes the margin between the two values. This is based on the idea that the value calculated from pi I should always be bigger than the value from the pi I if we follow the optimal reward function, because optimal reward function corresponds with the expert trajectory. The approach we are trying to take through IRL is implementing O2ARC to gather human logs when participants are trying to solve ARC problems, then training the agent to imitate the human trajectories.
So the next part is about decision transformers. I'm sure everyone here has probably heard of of transformers. Transformers are usually used for sequence modeling in NLP, but in recent years, it's been used for other stuff as well, like vision transformer. So now we have a new kind of transformer called decision transformer that tries to tackle the reinforcement learning problem using transformers. So you can think of reinforcement learning as just predicting a sequence of actions that leads to a high reward. So in this case, we have a transformer that takes in rewards, states, and previous actions. And from those, it's going to spit out a new sequence of actions that it thinks will lead to a high reward. So some of you might ask, okay, but we have other RL techniques, so why would we use transformers? Well, the first benefit of using transformers is, of course, that transformers have a pretty rich literature. There's a lot of papers and research done on transformers, and we can use those same concepts for decision transformers. But another more important reason that we want to use decision transformer is because of a problem in RL called the credit assignment problem. So this problem, you can think of it like this. Let's say that we're playing a game of chess. Let's say that we have an 80-move game, and somehow we lost the game. The question is, can you figure out the reason why you lost the game? As in, which moves did you make that were blunders? Do you know which moves that you made were mistakes? And do you know which moves that you made were actually good? The way for humans to do this would be, to do postmortem analysis on the game. We sit down with our teacher or with our coach, go through each move and just say, okay, this move is good because why is it good? Or this move is bad because of a certain reason. The problem in doing this with RL is RL problems kind of go through time, like in each time step you make a move. And at the end, you're just given one reward. So to figure out the credit assignment problem, you're going to have to propagate the reward back through time and figure out which move was a bad move. If the bad move was the first move, then you're going to find that it's pretty hard to figure out that the first move is bad, because you're going to have to look all the way from the end and go back to the start. But decision transformer actually sort of sidesteps this problem by using self-attention. Transformers are very good at remembering its past outputs. So by performing self-attention, it's able to just immediately assign credit to every single move at the same time. So that's one of the main reasons decision transformer is being researched and being used. And as an application to our task, what I think we could do is use a transformer and pre-train it on our 400 training examples. And using that sort of pre-trained data, we're hoping that the transformer learns some sort of priors that are useful in solving more data, in solving the test case. And for each test case, we could use some sort of random walk trajectory, or maybe some sort of heuristic to generate trajectories that we can feed into the transformer, and then use that to eventually solve the test problem. Another way that we could also improve the decision transformer is by adding a prompt to it. So from our few shot examples, we could try to create a prompt trajectory that sort of guides the decision transformer in its decision making. And this is presented in a paper from ICML this year called Prompting Decision Transformer with Few Shot Policy Generalization. Okay. And next we'll hand the floor over to Shape for abstract reasoning via logic guided generation.
So this is kind of a pretty recent paper from a KAIST lab by Jinushin. And this paper tries to tackle a very different approach to abstract reasoning problem. They are trying to use logics as a prior as opposed to the base knowledge in the ARC problem. And they are trying to tackle a different data set that's called Raven's progressive matrix benchmark for abstract reasoning progress. And we're going to talk about this Raven's progressive matrix first, because this data set is kind of different from our ARC data set. So there's a there's a standardized IQ test called Raven's progressive matrix. This is a very well-known IQ test for adults IQ. So this Raven's dataset is inspired by that IQ test. And in this dataset, we have more than 1 million images and 70,000 problems. And these images are algorithmically generated. These problems are kind of light in recognition and heavy in reasoning. And one big difference with the ARC problem is that there is no occlusion here. And the interesting thing is that since these problems are algorithmically generated, it's possible for a machine to do something. Like, for example, in the ARC problem, the best solution can reach only like 20% of the accuracy. However, right now the machine performance is like 59%. So yes, it's very hard, but it's probably not as hard as the ARC dataset itself. However, the human performance is 84%, so there is still a gap between the machine performance and the human performance. And again, as I told you, that Raven problem is not exactly ARC problem, because in each of the ARC problem, you curate every single problem on your own. However, in the Raven's dataset, you algorithmically pick and choose each element of the problem and make a new unique problem. Selecting the scene, structure, component, layout, and entity. So this is in right, you can see one of the Raven's dataset problem. This is like predicting which one is the next like correct output in this question mark. So if you spend some time, you can easily figure it out. And in this paper, they are trying to take a very novel approach to solving this kind of problem. So they are trying to tackle this reasoning problem into an optimization problem. By optimization, so first of all, how they do it is that they convert these problems into a propositional logic problem, and then try to optimize that propositional logic problem. So if you need some a refreshment about what propositional logic is, so this is the thing that we all learned in that discrete math class, that Paris is the capital of France and Paris has a population of over 2 million. So therefore, Paris has a population of over 2 million. So this was the propositional logic thing. The way propositional logic works here is that, for example, in this problem, you can see the color is same, the shape is changing, and sorry, the object is changing, the color is same, and the shape is same. So for the third question, the answer is the shape is changing, the size is same, and the color is same. So the logical answer is this triangle with the gray shape. And you can actually represent these properties as a propositional variable, like with and, or, and Boolean. So this is the connection to these puzzles, to these propositional problems. And interestingly, if you phrase these problems as a propositional problem, then you can actually solve them using then it becomes a problem called max set problem. And max set is a very well-studied optimization problem in optimization theory. So let's first talk about that a moment. So for example, max set is the problem of determining the maximum number of clauses of a given Boolean formula that can be made true by assigning truth value to the variables of the formula. So that's just a Wikipedia definition. So just to give you a concrete example, for example, in this clause, there's like 4 Boolean clauses, and no matter what Boolean value you put for x0 and x1, at most 3 of the 4 clauses can be true at the same time. So no matter what value you put, you cannot make all 4 true at the same time. So this is the solution for max set problem is 3. So you can at most make 3 clauses true at the same time. So max set literally means maximum satisfiability. This is an optimization problem, and you can use a neural network to solve this problem. And there was a research paper on StatNet, so you can check that out if you want more details. And in this logic guided generation, what they do is that first they embed the problem's images into discrete space, and they do that using a neural network that they self-supervise and train. And in the reasoning space, reasoning case, they use the StatNet. This StatNet is also another neural network, and they infer the rules as a propositional logic problem. And the reconstruction part is easy. It's another layer of network that predicts the answer from the embedding. So as you see in the abstraction phase, they take the image and take their attributes and convert them into these propositional variables. Then, yeah, you can see the authors have described in this figure. So reasoning to propositional variables, then abstraction and then propositional variable, then they do reasoning, and from the reasoning outputs, they just reconstruct the output. And the results, so I'm not sure why my image is not showing here, but
I guess their results are not very important in this topic.
yeah, so basically the result was that they beat every single previous work by 20% margin, and they far exceed the expectation of even the authors themselves. So the results was very, very excellent for this Raven dataset in this approach. So however, we have some thoughts on this work. First of all, this model can predict answer without looking at the options. So as you remember in this data set, so you can, this is actually a multiple choice kind of questions. You have 8 options and you get to choose the right answer. But this approach actually can beat all the other approaches without even looking at the other answers. So you don't need to train on it all the 8 data set. You just need to train on the right data set. The right answer. So, and the proposition, and the big thing behind is that they are trying to use the propositional logic as prior for solving the problem. However, this problem is kind of different from the ARC problem, as it doesn't make priors on the core knowledge. So it doesn't use objectness. It doesn't use, for example, agentness. It doesn't use the other core knowledge. It does use geometry, but not to the extent the ARC is using. So it's more like a traditional IQ test, and existing models kind of perform quite well enough, like 59%. However, we still think that if we can embed such logical priors into our ARC problems, maybe there's a way to go forward to solve our ARC problem. And it doesn't hurt to take inspiration from this as well. So yeah.
Thanks everyone for sharing some of the recent approaches. So I guess people listening here may have some questions on these approaches. If you have, please raise your hand,
Can I ask something?
pick up. Sure.
Okay, so let's suppose that you actually are able to learn abductive reasoning in this, for instance, in the data set that you were developing. So kind of given this grid, you kind of find the logic behind it and can apply to also, so you can also do the deductive part where you can also apply. And right in the start, you actually mentioned agentness, which maybe agency, so it's kind of like acting upon something. But I find it a little hard to extrapolate learning how to learn the rule behind like a 3x3, 4x4 grid to actually a real life application. So can you just give some examples of like how this abductive reasoning can be helpful for like real life systems?
Maybe we can consider like investing your money into some stock market and saying that you have limited knowledge of like how to make portfolios and how economic things like changes over time. And using those like limited information, we would like to find out like some good patterns how to like earn money in certain logics. And the solution may like include some understandable like components, so that since the economies are changing this way and the interest rates are increasing, maybe you have to pull like 20% of your money from your Bitcoin and just have it as as a cash. So instead of just classifying whether like buying or selling is necessary, we would like to provide like some reasonings on such application. And before we decide a certain domain, we would like to just drill down into the fundamental aspects of those reasonings. So we chose this problem set in small grid spaces. Does that answer your question?
Yeah, no, awesome, thanks. That was clear. Any other questions or comments?
All right. Then let me summarize our talk. So ARC is a challenge to build an intelligence with reasoning. Although we are focusing on like a small steps at this point, we aim to develop an intelligence which can like learn to learn. And during the past month, we have successfully created like two things. The first one is mini arc data set. Now we have like 150 like 5x5 grid like creative examples for like us to like came up with an algorithms, and we are able to design a tool to save human demonstration. The tool is called O2Arc. And we threw several events like Happy Arc Day, and we have invited some expert, like one from Cornell and one from Chungnam National University, and had a like enjoyable chat. And next Tuesday, we'll present our research into the idea contest through in Daejeon City. And we have shared like some hint to solve this problem: RL and inverse reinforcement learning and logic guided model. And for someone who are interested in this projects, we have actually a lot of opportunities. There are many like thesis topic. Technical wise, you can design a meta learning algorithm to pick what kinds of primitives you need when you see like a new examples. And you also can focus on finding a good language model and how to generate a program by using those like literatures. And also relational reasoning. In our problem, like agentness and objectness are very important. So there are some research domain that consider like how many objects exist and what kind of relationship exists between those objects. And the last one is more like interesting. We would like to like gather some more features. Maybe we can track like how human eyes movement on seeing like those examples through time. And the second part, we can also gamify like this data curation and problem solving processes. We would like to scale up these projects by having like more inputs. So people who are interested in participating in like this area, you can feel free to contact me. So the Happy Arc Day will be back. So we'll throw like another set of sessions to design like an IRL agent with the data set we have. And if you're interested in these projects, we have 2 meetings, one at E3 in Tuesday, 4 p.m. and the other one is in Friday, 3:30 p.m. at War Room. So feel free to take a picture of this slide and send your interest to us, then we can collaborate each other.